All right, so now let's go ahead and do something weird. Let's evaluate the limit as x approaches 5, and if you notice there's a little superscript there which has a minus. The way you read that is you say the limit as x approaches 5 from the left of this expression here. Now, generally speaking, the way these questions tend to be written is that they tend to pair those together because this expression on the right here has an absolute value. And since the expression has an absolute value, it stands to reason that we unfortunately have to evaluate it differently depending upon if you're coming from the left or from the right. All right, now let me explain this real fast. Okay, watch. What is the absolute value of 6? Don't write this down, just watch the screen for a second. What's the absolute value of 6? Bang up job, it's 6. What is the absolute value of negative 6? It's 6. Agreed? However, that's not the way it actually happens. What the rule actually states is as follows. We say that if the stuff between the bars is positive, just drop the bars. And if the stuff between the bars is negative, drop the bars and make sure to slap on a negative. So you'd say, actually what we're going to do here is drop the bars and slap on a negative. And you say, well, man, come on, the result's the same. Who cares? It's just going to give you a 6. And you're correct. But what happens is when there are x's, things get a little bit quirky. So let me show you a little example of that real fast. What is the absolute value of x plus 8 look like if you wanted to evaluate it from two different spots? Do we agree the magical place at which things occur is at negative 8? Because if you add negative 8 to the existing 8, that gives you 0. So what you have to think to yourself is, what happens when x is above negative 8? And what happens when x is below negative 8? Does that make sense? You got to consider this in two possible ranges. Or put another way, what happens when you approach negative 8 from the right, numbers above negative 8, versus what happens when you approach it from the left. See numbers below negative 8. Well, let's think about it. What you need to do in your head is as follows. Listen to me. Start plopping in numbers that are greater than negative 8 in your head. I mean, really, run through them. What if you put in negative 7? What would that make this stuff between the bars? It'd be negative 7 plus 8, which is positive. Try another one just for fun. What if you threw in a negative 6? Yeah, negative 6 would make that thing, again, be positive, and so on. So since that would make it positive, I can just drop the bars and call it x plus 8. Does that make sense? Now come over here. What if I come at it from the left? In other words, I consider numbers which are below negative 8. Well, I'm going to start plopping in numbers between the bars that are below negative 8. How about negative 9 in there? If you throw negative 9 in there, it's going to make it negative 9 plus 8, which is negative something or other. Do we agree? Specifically negative 1, but who cares? Just the stuff between the bars is negative. So as a result, what we have to do is drop the bars. That's ugly. But put a negative somewhere. And of course, if you want to distribute that, you can make that negative x minus 8. It doesn't matter. But that's the idea about absolute value. So people often ask me, how then do I do limits with absolute value? The answer is, you don't. You get rid of the absolute value, then just do the limit. So in this example, here's what we're going to do. We're going to approach 5 from the left. Well, hold on a second. Go right here and start plugging in numbers which are below 5. Think about it. Plug in a number below 5. How about 4? If you plug in 4, what happens? 25 minus 5 times 4 gives you a positive number. Again, just to give it another go, plug in like a 3. 25 minus 5 times 3, yep, gives you a positive number. So what we can now do is this. We can say, well, let's just rewrite this because I don't want to do this. I'm going to take the limit as x approaches 5 from the left of what is just plain old 25 minus 5x. See, because the stuff between the bars was positive, if you consider numbers below 5, I can just drop the bars. And then x squared minus 25 is on bottom. Now, as you might imagine, had it said coming from the right, you would have played a different game. You would have said, let me plug in like 6 here. 25 minus 5 times 6 is actually negative. Do you see what I'm saying? In which case, I would have to drop the bars and put a negative on the outside. But we don't have that going here, right? We have the from the left one, it just so happens. So we're going to continue as is. All right? Well, now where does that put us? Well, let's keep on factoring this thing out because hopefully we can see some stuff is going to cancel. So the limit as x approaches 5 from the left of what? Well, on the top there, we're going to yank out the 5, and then we get 5 minus x. On the bottom, we get what? X plus 5 times x minus 5. Now, this is quirky, right? Look, don't write this, but if this was a plus, most folks would be fine with those canceling, no problem. 5 plus x is the same darn thing as x plus 5. But what about these? Can I cancel these? You actually can. You just have to be mindful to keep a negative around. Does that make sense? They're the same thing. They're just off by a negative, so to speak. And so here we'd say, all right, that's going to give us what? The limit as x approaches 5 from the left of what expression? Well, now it is a negative 5 all over x plus 5. And since something canceled, I can just straight up plug in 5 now. Limit schlimits. It's negative 5 all over 5 plus 5, which gives us a what? Negative 5 over 10, or a negative 1/2. And there's my answer. All right, so be mindful of how to handle absolute value limits. All right, now this idea brings up something kind of fun. Let's go over here and start talking about discontinuities. All right, now let me move this over so we can see this a little bit better. Discontinuities, if you guys will notice, are simply places where the function does not exist, where it is not continuous. All right, so basically, for a function like this, if you have a polynomial on top and a polynomial on bottom, the easiest way to do what's called list all discontinuities and their types is to factor it. So let's go ahead and let's just dive in. I'll show you how we take it from here. Let's just factor it. On top, we get x times x minus 2 divided by what? On bottom, we get x minus 2, I think, times x plus 3. Let me double check that. Yeah, it looks good. And now if you'll notice pretty early on, something will what? Something will cancel. Once something cancels, that is an immediate jump off the page, you have something called a hole. Okay? Now a hole is also called, I'm going to be brief here and call it an RD. RD is an acronym which stands for removable discontinuity. Holes and removable discontinuities are the same damn thing. All right? And where does it happen though? It's where the thing you crossed out is set equal to 0. So incidentally, if you take the quantity x minus 2 and set it equal to 0, you'll get x equals 2. Does that make sense? So already, kind of just partway along, we've now figured out where we have one discontinuity. Awesome. Well, what remains is an x on top and then an x plus 3 on bottom, right? Once you get rid of the holes and factor, the thing that remains is the following. We have an x over an x plus 3. Now, when you take the bottom and set it equal to 0, that gives you what is called a VA, or a vertical asymptote, in this case, at x equals negative 3. Now, to be fair, that is sometimes called an infinite discontinuity. It's all the same. And to be even more fair, it's a what? NRD, non-removable discontinuity. So we'll say it's infinite slash non-removable discontinuity. All right? Now, if you want to be super awesome and just show something even better, let me explain something. I believe that the work on the page is, we'll call it adequate, but like if you really want to spice it up, which I recommend, do the following when it comes time to actually fill this out. We know that there is a vertical asymptote at x equals negative 3. We know there is a non-removable discontinuity at x equals negative 3. But what you can do is you can prove it. You can like drive it home through limits. Look, what happens is, why don't we take the limit as x approaches negative 3. Now we'll do it from the right. We'll do it from both sides, right? But let me show you how this works. Limit as x approaches negative 3 from the right is what? So right here, limit as x approaches negative 3 from the right of f of x. Well, watch this with me if you don't mind. If you plug in negative 3 on top, you'll get a number, right? If you plug in negative 3 on bottom, however, you'll get what? You'll get 0. When you get a number over 0, your best bet is to evaluate this by picking a number directly to the right of negative 3. I'll say that one more time. We got a number over 0, and therefore your best way at answering this question is simply by picking a number directly to the right of negative 3 and popping it in. So what's directly, think of a number line. What is directly to the right of negative 3? How about negative 2.9? Now watch what happens when we do that. We get negative 2.9 divided by negative 2.9 plus 3. Do we notice the top is a negative and the bottom is positive? I don't care what the actual answer is. What I know is the following. The limit as x approaches 3, the limit as x approaches negative 3 from the right is what's called negative infinity. As a matter of fact, I'm going to go ahead and jump the gun here. If you get a number over 0, the answer is always either negative or positive infinity. We're just trying to figure out which one. Similarly, watch, if you want to be, again, super baller here, just showing you know everything, limit as x approaches negative 3 from the left of f of x is found how? All right, well, pick a number directly to the left of negative 3. Thinking of a number line, what's a number that's just below negative 3? I would say negative 3.1, right? Just go a touch below it. So let's plug that in. That gives us negative 3.1 divided by negative 3.1 plus 3, yes? Well, that gives us a negative on top divided by, actually, it's a negative on bottom. So what do we notice? We notice that gives us a what? Positive infinity, right, guys? Because a negative over a negative is still a positive. Well, check this out. What I've done is really beaten to death this horse, which is that I already knew at the upper right-hand side of the screen that I had a vertical asymptote of x equals negative 3. I'm now just really like showing it over and over and over and over to the point that's kind of silly, right? And as a matter of fact, I got to tell you something. If you want to be semi-lazy, you can stop here. Because so long as you show that either one of the sides of the limits either shoots up to the ceiling, right, goes to positive infinity, or goes down to the floor, negative infinity, you have effectively solved the problem as needed. All right, but again, I want you guys to glean as many points as possible, so there's that. Now, uno más, right here. What if we are given what's called a piecewise function, and we're asked to find the value of some constant? I picked W arbitrarily. You can make it K or L or whatever, which makes this function I've written up on the screen here continuous for all values of x. Guys, this thing we should know is called a what? Piecewise function. Piecewise functions are very indecisive. He wants to be this when x is less than or equal to 1. He wants to be this when x is greater than 1. Fine. What we have to do to show that it's continuous for all x is that the following is true. The limit as x approaches 1 from the left of f of x, we are going to figure out what that is. And we are going to set it equal to the limit as x approaches 1 from the right of f of x. Now, I'll fill in a gap there in a second, but we'll leave that for now. So here's what you have to do now. You have to notice which piece to look at. Oh, and by the way, I should point this out. How in the world did I know that 1 was the magical number? 1 is what a lot of folks call this number here is the split-off point, right? It's the number that we're kind of focusing in on. It's the number that breaks up the piecewise function. So this piecewise function is like this if you're above 2. It's like that if you're below 2. Okay, 2 then is the point of interest. And this one is the point of interest. So let's give it a go then. What is the limit as x approaches 1 from the left of f of x? Well, I'm going to plug into that top piece, because that top piece is the piece we consider when x is less than 1, i.e. from the left. So that's going to give us e to the what? Just plug in 1. E to the 1 minus 1 plus 2 times 1 times w. Well, that's going to give us e to the what? E to the 0 power. E to the 0 power is 1 plus that bad boy is 2w. And to be quite frank, the limit as x approaches 1 from the left, that's about as good as it's going to get. Yes? Similarly, let's get the limit as x approaches 1 from the right. Well, that's going to give us this piece to plug into. So that's going to be the sine of pi times 1 all over 4. Well, that's going to give us the sine of pi over 4. Crap. What's the sine of pi over 4 again? Well, we think about our unit circle, right? We should remember the sine of pi over 4 is the square root of 2 all over 2. So we now have the limit from the left is this weird expression 1 plus 2w. The limit from the right is square root of 2 over 2. By the way, quick little side note. That expression is also f of 1. If you want to be a super badass and write this out with all this detail, then what you can do is you can say, not only am I going to set the limit as x approaches 1 from the left equal to the limit as we approach from the right, but I'm going to make sure it also equals the function's value at 1. Because the or equal to component is glued there, we say that's also the function's value at 1. But that aside, our next step is still the same, which is what? Take these two things and set them equal to one another. So here we go. That's going to give us 1 plus 2w equals the square root of 2 over 2. Now it's time just to solve. This is ugly, but that happens sometimes. Let's see. We got ourselves, just subtract 1 from both sides. We get 2w equals square root of 2 over 2 minus 1. And if I may make a recommendation here, since it's kind of split up, you can effectively divide by 2, but maybe think about it more like multiplying by a half. That'll make this happen quicker. So that goes away. We end up getting w, the constant, is what? Well, that's going to give us square root of 2 all over 4 minus a half. And barring feeling the need to mark it as a single fraction, what would that be? Square root of 2 minus 2 all over 4 or something? That is, I would say, a perfectly reasonable answer.